Oh, I did. So any portion of the aorta would be 100. Yeah. I'll know when I get home. I'll get out of here. So done is also excellent.
The steady state nuts.
Yeah, we have. And.
Yeah, a little bit.
Is your stuff like running super quick again?
Yeah, the residuals went back up. It went to E201.
It must be a unit mismatch.
I just switched out. I'm gonna do it right now.
Okay.
But, and then I'll send it in.
Yeah, that's so weird because I know the reason I'm so surprised because there was I got emails a couple years ago that said they were basically purging everything, or they're making sure that everything was in a consistent unit basis. Because yeah, when the units are off, it makes running the simulation so hard. But I guess they might have missed this one. I guess.
Is there a way to like kill this simulation?
You just gotta end task from the task manager. Just kill all of Sebastor.
Oh, just like exit out.
If you can just exit as Sebastor.
Task, like click the end task.
Yeah, or if you can just click the X, that's probably the best way, because then because you end task sometimes that you might have memory leaks. So.
Files. I'm
probably gonna do this.
I just uploaded my study.
I
I'm
think
gonna go there.
our thing for the
I want to like go with it. Not think about school for 2 hours, but
our level 4 got to 1,000 iterations, so I'm just gonna plot theirs in those and then put it in the center line, not center line, the grid independent folder.
and I have all my folders. I just need to.
That should be the last.
I need to do a set like a post process set sampling.
I'm actually text Martin, tell him to put it in his data file before he leaves. Because
I mean,
we could run it.
I was like, I can run. He already
If
did.
he has it.
Yeah. It would take me not even 20 minutes. Got the 8 core car. That's why, at least it's turbulent flows. It's wild to me like that. For our Reynolds number, it's like 3.5 million. And it's like taking me 20 minutes to run it versus like that 45 minutes for a Reynolds number of 4,000. On the ledger, gotta be close to me.
Thank you. That's it. No problem. See you guys. You guys all being going to commencement? Okay.
And we're all signed up.
I hope so.
Let's hope I pass. CFD, like the early, I died, but
Physical doesn't like me.
my grades on the men.
They forget about me for everything. So.
Yeah, is there a way, like, if it's like looking at GPA,
Yeah.
like we were like for him for sure, he should be with honors. Like, but he's not on the list. Like he's in Tau Beta Pi, but you literally can't be a member of unless you're like in that upper percentile.
Yeah.
But he's not on the list. Like, how would you?
Oh, really?
How would you go about like rectifying?
You can try contacting the commencement office, and so you can try commencement@fullerton.edu. I think they're the ones with the list.
Because they posted so anyone can like see it. But
Yeah. Or actually, it might be a little bit late, so I would maybe contact the dean's office directly. Don't actually know what.
because you get like a little sack for that, or
they just call you.
call you in a different section, right?
No, what we did last year, we didn't even name the names. They just said if you won this, if you're a magna cum laude, just stand up.
Oh, okay.
And then they clapped and then you sit there.
Okay.
Although there was a lot of complaints last year, so they may actually mention your names.
Do they do it cum laude, magna, and then summa?
Yes.
Yeah. There's gonna be like 4 summa.
Yeah.
Extra much, probably more than I know.
You guys, have a good one. See you at commencement.
Yeah.
Just to verify, the Neumann boundary condition is on edges 3 and 4.
For this example, yes. Oh, for the project, let me see. That I forgot. Oh, I forgot, yeah, because I was reading the project specs and then that description was from last year, because there's no diamond in this geometry. But I think it still is on edges 3 and 4. I said it in the
What's the value?
let me see. Project 3. The value is 10,000. Edges that were pretty sure it was 3 and 4. So the reference solution, you guys might have noticed, but the reference solution is at the bottom here. Oh, sorry. So the flux is going to be on edges 3, 4, 5, and 8.
Professor?
Yeah.
So the reference solutions look different for each graph? Or for
They are,
for
yeah.
section?
Each part has a different one. 1 and 2 will look pretty similar to each other, but 3 will look almost completely different.
Oh, 1 and 2 do look similar to each other?
Yeah.
Okay, that's,
I'm pretty sure, but
yeah, there's,
I forget. I think last time I taught this, they were pretty similar, but the reference solution should always be correct. And so
yeah,
so your solution should match the reference for each part.
okay.
Yeah. Mhm. Sort of on Roger, we're gonna be going over mostly part 3 today. But beside, I think it's not gonna take me that long, maybe like 15-20 minutes. Rest of the time will be just individual help on the project, so just like open office hours.
I had to figure out what was on the code, that takes a while, because once you write it out, it's easy, you gotta like something like.
Like even including that, like.
I mean. Saturday.
Maybe like, not based on like hours twice. It's not too.
Yeah. Yeah, I mean, that's just the first part.
Still,
That's
I mean,
like
yeah.
Right.
Maybe I could do 5 hours.
Yeah.
Yeah.
My efficiency goes way down.
Well, I think you got everything off story.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. For the last time, good evening. How's everyone doing? Good. Okay, so today we're going to go over just a bit more information on part 3 of the project. So on Monday, we had basically kind of went over parts 1 and part 2 of the project. Part 3 is a little bit different because you're going to be working with the Neumann boundary conditions, and so what I have, we're just going to go over that, just talking first. I have an example script, but I basically updated the example script from last time to include the Neumann boundary condition as well. And then we're gonna go through that. I think that'll probably only take me like 15-ish minutes to do. And then for the rest of the time, probably for an hour, I'm gonna go around and answer any questions that you guys may have on the code. So if you have specific questions, if you're running into specific issues, now will be the time to ask. Okay, so I guess before we start though, I know I do need to update the project specifications because I think the part of the instructions with the Neumann boundary conditions have to be updated a little bit. I have to include the actual value of the Neumann boundary condition as well as the edges that they're being applied on. So in the project specification that said the Neumann boundary condition is being applied on edges 3 and 4. That's a bit outdated. So the ones for this project are going to be on edges 3, 4, 7, and 8. I hope it was, or 3, 4, 5, and 8. Excuse me. And the value for the flux, well, the way to implement it is that you can set it up here. But if you want to match my images that are in the document, then I use the value of 10,000. Okay. But there's a way to write it so that it's flexible, and it'll update the reference solution as well. All right, so so I'll go do that after class today. Just make sure all that information is there. Any questions I can answer just in general before we get started for today? Okay. All right, so again, so the focus today is on part 3. I know maybe a lot of the class you guys are on parts 1 and 2, but I wanted to make sure I get this information out to you guys just because this is the last time we're all going to be meeting together. Okay. So just to kind of summarize, part 3, we talked about this on Tuesday. Part 3 is all about assigning the Neumann boundary condition onto our model. Okay. And so the Neumann boundary condition is unique relative to parts 1 and 2, because instead of performing a double integral across our element, we're instead going to be performing a line integral on one of the edges of our element. Okay. So I have this figure here that we drew on Tuesday. Right? And so normally we are integrating across the entire cross section of this vessel itself. But we're not doing that for the Neumann boundary condition. For the Neumann boundary condition, we're only integrating across that little fuzzy edge that I have on top. Okay. Most of the time, it's only going to be just on one edge, but there may be some weird situations where you might have to integrate over 2 or more edges. Okay. You're not going to see that on this project. On this project, the way the measure works, that the element only borders a boundary on one edge. But just be aware that in other codes, or if you go to expand what we learned in this class, you may have to account for multiple edges with a Neumann boundary. Okay. All right. So what we said last time was that the way to do this is to integrate. Okay. In particular, because we're doing a line integral, we only have one integration here. And so we're going to apply a 1D Gauss quadrature. Okay? Now, the key point to all this, because normally, normally the our integrand here, or the values of these parameters here in pink, right? Normally, all these functions here are a function of both of our parametric variables of xi and eta, right? Okay. Because that's how it is for our element stiffness matrix and our element forcing vector, or thermal generation function, I should say, right? So we're integrating out both of those variables in our element stiffness matrix. But for our Neumann boundary condition, we're only integrating one, right? And that's because the other variable, the one that we're not integrating, we're holding it fixed. Now, which variable that you hold fixed is going to depend, okay? That's kind of the general gist. Okay. All right. So the way we did this was that for this particular example problem here, we know that the Neumann boundary condition is being applied on the edge between nodes 3 and 4. Okay. And so what we said about this was that the value of eta is fixed here. The value of eta is being fixed at 1. Meanwhile, the value of xi is varying from -1 to 1. Okay. And so just like we normally do, we're not actually going to integrate this. We're going to integrate it using Gauss quadrature. Okay. And in fact, we're going to use a 1D rule of Gauss quadrature where we vary that one variable. Okay. So let me just kind of add an addendum here. So we're going to apply 1D Gauss quadrature on the xi variable. Okay. While keeping the value of eta fixed. Okay. All right. So we did that by hand last time. And so what that looked like was that, first of all, we had to compute the length of the edge. Okay, so to compute the length of the edge, we just use simple kind of a distance formula for that. Okay. We had the value of our flux. Our flux value in this case was 5. Okay. And then we performed our integration here. Okay. So the only because our length is constant, because our flux value is constant, the only function that we're actually integrating are just the shape functions themselves. Okay. And since we're holding one of the variables fixed at a value of 1, that means we're only integrating over that other variable psi. Okay. And so for a 1D Gauss quadrature, we usually use 2 points. And so those 2 points are -1/√3 and +1/√3. And so we're basically going to evaluate our integrand, which is all 4 of our shape functions at those points. Okay. So we have this first entry here, N1 through N4 evaluated at xi is equal to -1/√3 and eta is equal to 1. And then we have the second evaluation where we evaluate all 4 shape functions at xi is equal to +1/√3 and eta is equal to +1. Okay. And so you add those two together, and what we get is 0, 0, 1, 1. And then we multiply it by the length times the flux times the -1, and this is our contribution. Okay. So I know I went over that fairly quickly just because we did that last time, but I wanted to give you some context for the code that I'm about to show you. Okay. Okay. Any questions on just this part here? Okay. All right. So let's look at the code. So I updated the isoparametric example code that we had that we went over last time. And so that's available to you on Canvas. And so if you go to the Canvas site, you under code, if you look at the isoparametric code example here, you can see that I had just updated it yesterday, just because I worked on it yesterday afternoon. Okay. So this is the one that we looked at last time, but compared to the one we did on Tuesday, there's a section at the end that I added for the Neumann boundary condition. Okay. So if you want to look at how it's implemented, you could download that. Or you can just wait for the next 10 seconds. Okay. All right. So this is the code. Okay. So this is the isoparametric example code that we went over on Tuesday. So you can see the top section is still the same. So we do the Gauss quadrature on the for the element stiffness matrix, and so we had our 8-step process. Okay. Now the code that I added was down here, starting on line 78. Okay. So what I'm going to do here is I'm going to go through each section of this code, kind of explain what's going on, just so that you know. So a lot of this code here you can use not verbatim, of course. There's a lot of differences between this particular code and the and the project, because the project is a triangle, these are squares, but the same idea will apply. Okay. So the basic idea with this code is to do the 1D Gauss quadrature on that edge, okay? But you want to make sure that you choose the right edge, right? So for this example, we know that our value of eta is going to be fixed at a value of +1. Meanwhile, we're going to be integrating the value of xi from -1 to 1, okay? And so that means we're going to set xi at, so these two values right here, these are the Gauss, this is the Gauss point for the first one. The values of the first Gauss point, these are the values for the second Gauss point. Okay, so first Gauss point, we have a value of -1/√3 for xi, and a value of +1 for eta. And for the second Gauss point, we have a +1/√3 for xi, and a +1 for eta. Okay, so you can set those kind of from the beginning. All right. The next thing that we have to do here is we have to evaluate the shape functions at the two Gauss points. Okay. And so here we have N1, N2, N3, N4 evaluated at Gauss point 1, Gauss point 1, Gauss point 1. Okay. So you can see that these formulas here are the formulas for our shape functions. So we have 1 minus xi times 1 minus eta all divided by 4 for shape function 1. Okay. And you can see here that I'm plugging in the values from the first Gauss point up here. And I have the same thing for the second Gauss point. So N1, N1G2, N2G2, N3G2, and 4G2. Okay, so all these are the same formulas, just the only difference is that I'm plugging in the second Gauss point as opposed to the first one. Okay. All right, from there we can arrange these into vectors, and so I just simply arranged these values into a column vector just to make things a little bit more convenient for us to add in a bit. Okay. Next thing I did was I computed the distance, and so I know that this is between nodes 3 and 4, and so I computed the physical distance between those nodes. So it just simple distance formula here, square root of x3 minus x4 squared plus y3 minus y4 squared. Okay. I have the flux contribution, which is 5, and then all I did from here was I added our two shape function vectors here. Okay. These are our shape functions that were evaluated at the Gauss points. I multiplied by our distance divided by 2, multiplied by the flux value. Okay. So this right here is basically the code version of kind of the example we just ran through by hand. Okay. All right. So the general steps to this code is, establish the Gauss points. You have to be really careful about which point is going to be fixed and which point you're going to be integrating over. Okay. You're going to evaluate the shape functions at these Gauss points. You're going to assemble into a matrix, compute the distance, and then finally add the contribution to the element forcing vector according to all of the above. Okay. All right. Any questions on that? Okay. All right. So of course this code here is for a rectangle, but for a triangle it's a little bit different. Most notably, your values of the Gauss points are going to be different. Actually, I know Nick asked on Tuesday, what are you going to do for the slanted portion of the triangle? So let's talk about that now. Project. Okay. So for the project, that we, instead of a rectangle, we are integrating over a triangle, right? Instead of a rectangle, we're doing a triangle. Okay. So when you're doing the Neumann boundary conditions, the Gauss points are actually going to be located at these locations here. Okay, and the values of the Gauss points are going to depend on which edge that borders the Neumann boundary. Okay? So if it's edge 1, 2 that borders the Neumann boundary, the Gauss points are given by the following. So the first Gauss point is √3 minus 1 divided by 2 √3, comma, √3 plus 1 divided by 2 times √3. Okay, and the second Gauss point is given by the following. if edge 2, 3 borders the Neumann boundary condition, you're going to use these Gauss points here. And if edge 1, 3 borders the Neumann boundary condition, you're going to use these Gauss points. Okay. So just be aware that, when you are doing the Gauss quadrature on a 2D triangle, that the Gauss points are going to be different. Okay. Now, but then that begs the question of, how do we know which edge borders the Neumann boundary? Okay. And so for that, I think this is probably the part of the project that kind of confuses a lot of people, is we need to determine, which edge of the triangle is the case. Okay. Now, normally, for more sophisticated finite element code, there are more sophisticated ways to do this. But this is kind of a little bit of a roundabout way. I think it makes a bit more sense, at least logically. But just know that there's other ways to do this as well. Okay, so if you open up the starter code for part 3 and you scroll down to the part where the Neumann boundary conditions are, you'll see kind of this code here. So I wanted to spend some time today kind of explaining how this code works, or at least kind of the logic of how to approach this part of the code here. Okay, so first thing you're going to see is that there is a for loop. Okay, so the for loop is going to move over all of the edges that have Neumann boundary conditions applied to it. And then immediately we're going to call these two functions. So one is called find nodes, and another one's called find elements. Okay. So the find nodes function, this is a function that is applied on the mesh itself. Basically, this lets us, this allows the mesh to tell us which nodes are connected to this particular edge. Okay. So the way it works is that we feed an edge number into this function here. We feed it the mesh. And this gives us a list of the node numbers that are attached to that edge. Okay. Because remember, and actually let me run this code just so that you can see. Right. Remember from Tuesday that, when we have our mesh, every node in the mesh has a unique ID number. Right. Right. Let's zoom in. So you can see here that every node has its own ID number. But we're interested in, what are the nodes that border a specific edge? Okay. So let's say that we have a situation where this red line right here, this is where we're going to apply a Neumann boundary condition, right? So we want to get a list of all the node numbers that are attached to this edge right here, right? So if we read this off, this will be actually quite nice. So this is node 31, node 32, node 33, 34, 35, 36, 37, 38, 39. Okay. All these nodes are attached to this edge on the right. And so they're going to be the ones we're going to be applying the Neumann boundary condition. Okay. Okay. So that's good. So that's what this find nodes function does. So this find nodes function basically, you give it an edge, and the mesh will tell you all the node numbers that are attached to that edge. Okay. Next, we're going to use a function called find elements. Okay. And what this function does is that it searches through. Basically, you give it a list of node numbers, and it gives you the list of elements that are attached to those nodes. Okay. So this is going to give you a list of element numbers instead. Okay. Because for all of these node numbers here, there's also a corresponding element that's attached to it. So let me go to this image here, maximize it. Okay. And so for every node that's on the boundary, right, we're going to return a list of elements that are attached there as well. Okay. So we're going to get, in this case, element 255, 309, 262, 261, 244. All of these elements are bordering this boundary right here. So these two functions right here, both the find nodes function and the find elements function will give us a list of all of these elements here. Okay. Okay. Now, the next thing that you have to do here is you have to obtain the Neumann value. So you have to obtain the value. And so for this, you're going to make use of this Neumann values vector that you're defining up here. Okay. So this is a vector. This is a data structure that we've used in our direct stiffness problems. And so, I won't delve too far on that. Okay. Okay. Then we come to this element, which is probably the most confusing part of the code right here. Okay. Okay. So inside this element loop right here, there's two things that we need to determine. First thing that we need to determine is, first of all, do we have an element that has a full edge on the boundary? Okay. Because if you look at our mesh right here, right, we have a lot of elements that are just touching the boundary at one point, right? So if you look at, for instance, element 309 right here. Okay. Element 309 technically is touching the boundary, but it's only touching it at one location, okay? At one node. So element 309, we would not want to count this into our Neumann boundary condition because it only borders on one node, okay? Because we need to have a full edge of our element on the boundary in order to do our line integral, okay? So basically, we want to look for elements that have at least two nodes that sit on the boundary, okay? So that's what we're going to do here. Okay, so in this loop, the first thing you're going to do is you're going to compute the ID numbers for the elements. And so just like before, you're going to use the connectivity matrix for this. Okay, so make sure you use that. Okay, next thing you're going to do here is you're going to check and see, out of the three nodes that are in this element, how many of them are on the boundary. Okay, we know for sure, just based on what we've done so far, we know for sure that at least one of the nodes on this element is attached to the boundary, okay? But we only want to continue if we have at least two nodes on the boundary, okay? Okay, so it goes like this. So let's say that, at this point in the code, you've defined N1, N2, N3. N1, N2, N3, these are the nodal ID numbers that you've used, right? So these are the connectivity matrix, okay? Okay, so you want to find out is N1, N2, N3, are those actually on the boundary, okay? Because the most likely scenario that you're going to find is that, N1 may be on the boundary, but N2 may not be, but N3 is, okay? So the way we do that, we're going to make use of a special MATLAB function called isMember, okay? So what isMember does is that it takes this entry right here, which is a number, and you feed it a vector as well, okay? So if N1 is a part of this vector right here, if it's a member, then this is going to return true. Okay. And if that returns true, then we know that this node is on the boundary, okay? And so to mark that this node is on the boundary, I've done kind of like a you can almost think of it like a stamp card, okay? And so the stamp card is this vector right here, and if it's on the boundary, we're going to set it equal to 1. Okay. And so what you have to do, so I've already written the first check for you. You're going to do a similar check for the second node and the third node. Okay. And I've done this in a very particular way because the way that these are numbered here. This is like node 1, this is node 2, and node 3. Okay. If you go back to our project specifications, you can see here that I have node 1, node 2, and node 3. Okay. Because the second thing that you need to determine, so let's say that you found an edge here, or you found an element with two nodes on the edge, right? The next part is to determine which two of those nodes are on the edge. Okay. Because depending on which two nodes are on that edge, it's going to change your Gauss points, right? So so let's say that if nodes 1 and 2 are on the Neumann edge, you're going to use these Gauss points here. If nodes 2 and 3 are on the edge, you're going to use these Gauss points. And if it's 1, 3, you're going to use these two. Okay. And so if you go back to the code right here, there are different conditions for, let's say that the boundary edge is the diagonal of the triangle. So that is nodes 1 and 2. Let's say the boundary edge is the horizontal edge on the bottom. So that's nodes 1 and 3. And if it's the vertical edge, that's going to be nodes 2 and 3. Okay. And so in all these situations, you're going to do the same thing. So you're going to compute the edge length. You're going to set the Gauss points. Okay. Okay. And then once you set those, then you can actually do your computations down here. So that's this right here is kind of similar to what we did at the beginning of class today. Okay. So once you kind of reach that point in the code here, you'll have your Gauss points satisfied. So then you would then compute the values of the shape functions of those Gauss points. Put them into a vector, compute the distance. You computed the distance already, and then you make the contributions to the element forcing vector. Okay. So that's kind of the logic of that part of the code right there. So it's, you know, I think in concept, when you look at it just from the calculations that you're doing, it's not that difficult. It's just kind of knowing what condition you're in and just kind of understanding how to work with the mesh itself. Okay, so hopefully that explanation kind of helped a little bit in terms of kind of what kind of my logic in that part. Okay. Any questions on this here? Okay. All right, so I'll go ahead and leave this up, or I'll leave the example code up. So that's all I had planned for today. And so we have about 50 minutes left. And so if you have questions on your code, you have some things you want me to look at your results, or if you have an error that's coming up, just raise your hand. And I'll make my rounds today to help you guys out. Okay. If you're on Zoom, just drop something in the chat. I'll come back to the podium every 10-15 minutes or so.
I think so.
Yeah. Yeah.
This
That's
doesn't
match.
match.
Looks like it's-
Yeah, it's pretty much the same.
I think that's twice. Right. For the second part, I don't know.
It's a great observation. So that's always a problem with corner nodes too, because they're existing on two boundary conditions. Actually, if we read the project spec, there's one question now. And it's implemented, you could get a very small.
So none of them
Yeah.
or solutions.
Oh, tiny
Yeah,
amount.
that's
So
why
I don't know that.
because at least internally, they almost didn't doing the exact same. But depending on the order, you apply to that big boundary, it just
So many diversion.
very small.
It should change.
Overall, you can see visually it's to it. You have to like really squint it and place to see it.
Yeah.
But that's the first. That's.
It looks almost the same.
Yeah.
It's just like the big issue.
I think it's often like this, and so I'm pretty confused if this is working on mine.
Yeah. Well, it's not due, but I should still work on it. That's.
Yeah, so I'll tell you the same thing. So what can happen sometimes that if you notice.
So, thank you.
Okay, what was your project for that class?
So there's a keyword solution, that's
What was your project for that class? Yeah.
Everything else, everything else.
Something about Euler's formula.
Yeah.
I don't know.
I honestly don't remember. It was something pretty easy though.
This edge.
Did he, yeah, I think so. Yeah, because he using
Technically, that node you could apply.
present.
Yeah, he talked about it. Yeah.
Yeah.
Tell him about taking.
Yeah, I was,
Or was it bad?
I don't remember.
Okay, yeah. No.
I say.
I mean, I could send it to you if you want. I think I sent it.
Yeah, if you don't, yeah.
So it's short.
So he just wants us to make like,
Okay.
it's like Euler's method, there's like a table that
Yeah.
kind of spits out.
This looks really good.
So he wants us to kind of do that in, so.
Sure.
Oh, so
Yep, the only things, remember, IDP, IDP2, those are.
There's something like we do that, but we'll project. Do you remember that?
Right now,
Yeah, I remember that I kind of.
It's like it's like a better Euler's, basically, that's like. It's a bit more accurate. Wants us to like,
Okay, but that's.
basically put it so we can get values.
So you're already doing another portal. Same as up here. But you just have to do one here.
Well, they already went through the.
Exactly.
But, okay, let me reset the.
Exactly.
Copy that, paste it, and it's okay to leave the link.
Yeah,
This is.
that's perfect.
Okay.
Yeah.
I think I'm doing the first part right, so I'm just checking the figures, right?
Yep.
That makes sense. I think they match up pretty well.
Okay. Good.
Okay, so that means.
Perfect.
How do I know if the second one is?
So there's, you can see here that every time you run the code, there's an error that comes up.
Oh,
So basically what I do is I subtract your solution minus the reference solution. And that's just the total.
okay,
So 10 looks like it's big, but remember that all the temperatures are gonna be ranged anywhere between 25 and 100, right?
Mhm.
So across all your nodes, an error of 10 is actually pretty good. So if you visually look at, probably the 4 and 5 are updated now. Usually, parts 1 and 2 look very similar, thermal generation. Oh, so there is a little bit of difference. So you might want to check how you're implementing the thermal generation. There's a little bit of a difference in kind of these areas. So, yeah, just check how you're doing the thermal generation, right?
Okay.
You may want to try to refine the measure a little bit. I know you probably course it to make it run faster. And maybe make the elements a really smaller by.
Okay.
Yeah.
Yeah.
You don't have to define that.
Yeah.
I put it up there because I was playing around with the idea of sometimes
Right. So you got.
change the code or do it.
Exactly.
I just want to. We can have it down here. Yeah.
No, give me like 10.
Zoom people on back.
Yeah, you shouldn't get one error.
Add this point. Yes. So let me. So that's this part right here. So actually, let me bring up part 1 of the code because I think that might be a little bit easier to explain from there. I've downloaded this story code multiple times. Okay. So you're doing the Gauss quadrature, right? And then each Gauss quadrature is going to contain a piece of the element stiffness matrix. And so in this part right here, I want you to add that contribution from this particular Gauss point to the element stiffness matrix. And so the element stiffness matrix is this data structure right here, KLM, right? And so you want to do KLM. Okay. I'll let you determine what's in here because we've kind of done this parts of the code before back when we did trusses and springs. Okay. So you want to add this contribution to this particular element. Okay. And then here you're going to add to it your contributions from this Gauss point, right? So that's the multiplication of the shape function derivatives in the physical space as well as the thermal conductivity. Basically, step 8 of this part right here. This part. So you want to. So this right here. This is the contribution from this Gauss point to that element stiffness matrix, and you would add it to KLM using a syntax kind of like this. Does that make sense, Roger? Okay, cool. Yeah. So there's 3 inputs to the KLM matrix. So the first 2 is 3 and 3, right? So you know, for our triangular elements have a 3 by 3 element stiffness matrix. So that's there. The third dimension of the KLM here corresponds to the fact of the number of elements. Okay. So we're basically computing each element stiffness matrix and storing that for that particular element. I don't know if you remember, we talked about this maybe like week 7 or week 8. We use kind of the exact same data structure for our truss and spring codes, where you know you can think of each element stiffness matrix as kind of like a 2-dimensional, like a paper, right? And then we're computing them for each element. So you can almost think of it like, you know, each element stiffness matrix is an additional sheet of paper that we're storing for that element, and we're kind of filing it away inside a file cabinet, right? So kind of the analogy I think that's useful in your head is to think of these as kind of like, you know, files or papers that you're filing away. And so that third dimension there corresponds to the element number for the element that you're computing the stiffness matrix for. Yeah, the first 2 are just the size. So you know, this dimension right here is 3. This dimension right here is 3. And then this dimension that goes into the page, this is the number of elements. Okay? Because you're gonna have one element stiffness matrix for each element in your in your mesh. Yeah, look back at our truss and frame codes. You'll see that, you know, we use this exact same structure there. Exactly. Yeah. Perfect. Yeah, those X's are replaced by something else. Just you know, look back at our truss and frame code. You'll see. But that's exactly the right idea. Yeah. Yep. Perfect. Yeah. So basically, you know, we did kind of a version of this, right? But instead of connectivity layers. Okay, so I'll kind of do that. Yeah, you have to do it. Oh, still use connectivity. So, yeah, no, basically, so we're looking at ideas. That you wanted to be ID numbers for the node that are and those ID numbers, we kind of use them as kind of rows and columns. Oh, we have the name that node one, I think from there, and so it's this on the entity, they're almost there. We're gonna add. Okay, so on, so, yeah, that was just. Oh, okay, so we don't have to worry about. So we just here we have done it. Yeah. So the reason we did that was in the rows, each node had more than one. Each node had an X deformation divided by the.
You know, class here, or what class is not?
So 500. Oh, cool, yeah.
I take that.
Classes, probably, we can have where we have X and Y definition, probably some. Yeah, like, one. Oh, okay. But here, we can do it. Okay. We've got that, and then, seasons. I wasn't sure, creating this.
Yeah, so for that one, you're gonna get the traditional valve. So the way we're doing traditional valve condition is pretty a bit different. Because in frame or the ratio of valve condition, you only have one fixed. So we said equal to 60. Here we actually have non-zero. Oh, yeah, I'm not here. I got it. That's what I say.
That went to 600,
So yeah, here. Instead of the ratio of edges, it's ratio of value. You need that value, that value, okay, that value can go here. That's the one that's set in right inside. Okay. Okay, so. This is. That wasn't exactly sure how this would. Yeah, so that function, that works the same way as kind of. Because we know what Edward kind of got, we just need to know the node. Okay, so that finds the nodes. Exactly, so this is actually a vector, so this is a vector, it's a list of all the nodes attached to this. Exactly. And so, so here at this point, we're actually. We're using all of these nodes. And these nodes will be releasing that equation for setting it. You get the key numbers, this is which one to go. You're zeroing out that row, you're setting that on this one, yeah. The only difference is that like for the frame program, you set it to 0, right? But instead of 0, we have to set it. No, because of class under. Okay, so the only other thing that you do is figure out kind of what's row or no. Okay, but all the information there. And that this basically just set to. Well, inside smooth. Yeah, and so you know, you reference that somewhere, so you can use that information. Oh, okay, yeah. Okay, well, thank you, sir.
Yeah,
That's one.
we'll do that. And how I had it but it's not like about just bidding X1, X3, or negative go. That's one and these are. That's X3, yeah. It makes it all that. XP, why we so permitted for. Did you get something else here or is it from?
Yeah. I don't know, I shouldn't scroll down.
It's a lot. But on the.
Yeah, so I was just telling Trevor, so in this case, you don't have +1, every node here is going to block it.
Okay.
So the reason we did +2 each node in that case had more than one. You're going to work. So this actually looks.
I'm trying to figure out how small error.
Oh, I forgot it. That equals to EK now.
Yeah, so
Okay.
you need to save it here, but you need to be really careful. You know, I was trying to arrive at that earlier, that, this needs to be K on this. But we need to reference a certain part of this.
Okay.
So the structure of the KLM matrix is that it's a 3D matrix. And the first two dimensions here, that's what you reckon.
Yeah.
So the way to kind of interpret this is that each restoring every element. Restoring as like a sheet.
Yes.
And so, but then the number of sheets that we have. Yeah, so this third dimension should correspond to this.
You have the question.
And then this, what you're computing here, based on the size of the vectors, is, this will be. Oh, and so you have to kind of incorporate that little business.
Yeah.
That's kind of thing.
Oh, this would be like. How long does this be?
And what's not. Okay. And same.
Now.
Yes. And so you hope, well, it's like you actually, if you look back at our small plane code, you should see this, that line there will translate. Yep, you got it, Roger. That's it. Okay. Oh, okay. That's basically.
Is that cool?
Yeah, that's.
Yeah, that's cool, just cool, yeah. Yeah.
The physical coordinates. Yeah. So we computed those up here. So they're up here. Yeah, those are. So the way I have it down there, so I think I had it as a chord matrix, right? So that chords matrix has a specific format that actually matches up with those two. But you have the values of x1, x2, x3, y1, y2, y3. It's just arranging that in that matrix with this. That would be this matrix right here. This is a chord. I mean, of course, there's four here because this is for rectangle. Let's just put that in. Exactly. Yeah, so that would be the chord matrix. Yeah.
Right now.
Yeah.
Right now.
It is a vector.
So then you would get this, your FE would also be a vector.
Yes, Fe is a vector and K is a matrix. Yeah, so that vector right there is a vector of just the shape function itself. So that's step. I forget the step. Remember, our shape functions for the triangle are very simple. So n1 is just xi, n2 is just eta, and then n3 is 1 minus xi.
It's a bit.
Oh, wait, it's.
We can all be this.
Find the null. Yes. Yeah, so that's exactly what the connectivity matrix is for. So connectivity is to get you the nodal ID numbers that are connected to that particular element. Yeah. Mhm.
Professor,
It's part of the kind of.
hello, Professor, can you hear me?
Oh, yep.
Yeah, Professor, I will just send you the message. It's for the K element and the Gauss point. Can you
Okay.
just check it once? I've edited it.
Did you send me an email? Sorry.
No, I just send you the chat box only. Zoom chat box.
On the chat. I don't see anything on the chat. Oh, sorry. I missed it.
is for the Gauss point, like the last part of.
Okay. So it's almost there, but instead of the chord matrix, you know, that should be the index for the element itself. So think about, you know, you're looping over all the elements there. How do you use that kind of information in that? But it's 95% there. It's just instead of the chord matrix, you should replace that with something else.
Oh, I just send you the another one message. You can see the last message. Is it the one?
I only see the one at 6:04. I don't see another one after that.
Oh, okay. Let me send you again. Okay, just give me a minute. Yeah, I sent it to you.
Not IG, because remember that last index there has to do with the element itself.
Oh, okay. Yeah. Let me check. Okay.
Yeah, so IG corresponds to the number of Gauss points, but remember you're saving this information for the element. And so the loop index that has to do with the element is this one right here.
Okay, Professor. Yeah.
Yeah. Mhm. Yeah.
What's that acceptable error?
Honestly, it kind of mesh.
Or two?
Okay.
It looks very similar. I'm not sure if you said the reference.
Yes, reference is always good. There's always gonna be some degree of error.
So let me see part one first.
Yeah. Honestly, it doesn't change all that much. The thermal generation, or I designed it, so it's kind of not really.
So we can make it bigger so we can.
You could, so basically, so do you see this variable for the generation?
Yeah.
You can just
Crank it up.
crank that up. So we can like. Something like that.
Oh, okay. Oh, okay.
Yeah, so there, it looks like there might be an issue with that.
Okay, cool.
But that's how you install. So I'm surprised that, well, it's pretty stable, actually. See at 3,000 and something times 10 to the fourth.
Okay. I think it means. Oh. There is a figure,
Yes, you do. Yeah, you do need to use a for loop to assemble a Kegel. Yeah, I believe the for loop's already there. You just have to use the one that's there. Yeah, Janish, yeah, that is the correction. Oh, no, you shouldn't need a nested one. You can do everything. I mean, I guess technically you could do it with a nested for loop, but I think this is a case where just doing it with one for loop is probably the easiest thing.
Professor, so the kind of thermal generation are calculated and our reference should be the same. Yes.
Mostly the same, yes.
Mostly the same.
Yeah.
So there might be some solution.
There might still be some small differences, but for the most part should be the same.
Okay, thank you.
Yeah, it might be bigger differences with higher thermal generations because you're basically the linear solver. So when you go to solve the linear system, I think the one for the reference solution uses a little bit more of an efficient method.
Oh, I see.
We're just using just basic backslash.
Yeah.
So I think So when you have low numbers that there's usually no difference between the two, but as you crank the numbers up, there's a linear solver issue called stiffness. So if you got a really stiff linear system, then that could cause some differences depending on which method that you use. So that's why I don't recommend cranking it up too much because it might be hard to get them to match. But maybe something like 10 or 100, I think is okay to do that.
Exactly. Oh. So the way I read this was the same here. Remember the way in one step. And because there's else, there's guaranteed and usually. So what I did was I'm just that same.
Oh, here it is. This and
X G1, G1, and then sort of G2, G2. And then down here, that shape, the shape function is almost the same. The only thing is that shape function died. And one way that it works out. You may, some people may say this is kind of a very probably. In the end, what you're going to check when you add up the shape functions together, you're going to get a vector that's 1, 0, 1, 0, 1, 1. So you can do that. This is kind of more. You would need to do it this way. Have a cluster and a chance. That's big. But since it's a constant, there's a simpler way to do it. It's kind of a more traditional. Yeah. Yeah. Oh, that might have been.
yeah, so it just means I know.
That's what that is.
Yeah,
Yeah.
That's what, yeah, okay.
One comma, one comma.
Yeah.
But so you're basically it's gonna call each index, so it's gonna be like comma, one comma, underneath. Yeah, so when you want to comma that's doing. It's all 70 something.
Exactly. So you're defining what way to do it.
Yeah.
Remember, F will just fix the same vector. Actually, when
It doesn't fix it, we blame Jerry.
Yep.
Question. You tell Jerry that you hit the bugs. You know, Jerry, this can also be different.
Yep. No, that's perfect, Janish. Yep.
Or
You do get the picture.
Yep.
Does your Jacobi a matrix?
It does.
With the Gauss ones?
Oh, with the Gauss points, no. Wait. It does. Well, for the triangle, technically it doesn't because all the shape function derivatives are the same. For the rectangle, it does change because the shape function derivatives actually depend on the Gauss points. So because all our shape function derivatives for the triangle are constants, technically you have the same Jacobi matrix for all three.
Okay, so problem not the Jacobi. I can't figure out why I'm not getting. Have that issue.
I need to this solves that.
That's crazy.
For this part too. Um. Get better energy. Yeah. Was nice.
Oh, Gary.
No.
I think it is wrong.
Okay, so the FLM here, the FLM is only gonna be a one-dimensional, it's just a vector. And so remember, each Gauss point, you're just adding two. So there's actually no need to actually have this part right here. Does that make sense? So, because it's all going into the same pot.
Oh, right, okay.
And then, and so same thing. So you have, you're computing that this quantity of 3 Gauss points, but you're just adding them all up together. Right, so like this, basically, you're just adding those things there. Okay. And the other thing that you have to add here is that, you have to assemble this too, because every element has its own element forcing vector, but you need to add it into the global forcing vector too. So you need to have that part in this. Here. Okay. Right? So you have like an F global.
Oh, the other one.
Is equal to, F global parentheses something is equal to F global parentheses plus FLM. Yeah,
Got you, okay.
It's fixed.
Oh, I'm sorry, so yeah, so actually F element is a 3 by 1, right? So it is actually there's two things there, two dimensions, but that quantity. This quantity actually gives you a vector. And so this thermogen, this is okay. So you want to make sure that this is the appropriate thing to, because S this thing is a vector. Right? So this, you should get a 3 by 1 vector from this automatically. And so this should be because you're adding the 3 by 1 vector to the 3 by 1. Yeah.
Here's all over ready. This is the value for the, I think the 167, I think.
On the, I just, okay, the answer to that, I don't want to run there, yeah, it's work. Yeah, okay. So going back to the one, kind of, I don't think they did it. This, yeah. We're not after this thing. There's another three.
Not necessarily. So this is kind of a new thing here, but in our right and trust code, there's no, well, we did have this.
Yeah,
Instead of actually saying something, just said this was zero. So here we actually have non-zero.
Yeah, and that.
And a non-zero version for time.
So.
Okay, so actually, so for this part of the code, you have to read in kind of what the value is. This loop that you want to solve.
Okay.
And so instead of head is right, you should actually change the value. Okay, that's gonna be the nursery value, and then you're gonna incorporate this. Here's, okay, and this gets incorporated. This tells you the row. You're gonna redo that right here.
Okay.
You wanna make sure that you're modifying the right things like forcing vector on the same row.
Okay, so for, so they're. So D is.
Yeah.
I would use the time.
Exactly.
Oh,
Yeah.
okay.
Yeah.
Okay, thank you. Yep. Pretty.
Oh, good.
It's pretty consistent.
Okay.
It's not too bad.
Yeah,
Compared to like the power.
Yeah, that's great.
It ain't too bad.
that's great. Nice. Yep. Oh, thanks. Okay. Yeah, so defib, so we want this to be. So defib right.
So I just feel like is,
Uh,
but like the actual white shirt.
No, I think saying no, it's what, so you know, the change.
This way, what did you do?
Smart job. But we go. So, when you get a great job, yeah. Yes, I know, why have you done that?
Yeah. So you have.
We can part two, we can part two.
Oh, they're just originals.
So this one has. And now one by.
That's what's that.
This is really down. In order for this, in order for this. Should get.
Oh, yeah, we just.
Same thing.
So I have to. And we want to end up with a 3 by 3.
I don't know if I.
So think about which one should we transfer out. Okay.
You're gonna get caught.
Are you sure?
And then you build.
Yeah, the.
Sure, I'm checking it out.
Oh, too bad. Did I know the problem? The code is really concerned. Make sure that it's actually. Yeah, it's good. It gets stuck on the first. You can see how you. You're in the factory. Or they're just. It's a. That's why.
Yep. Yeah, no, that setup is correct, Roger. So basically what you're doing is that you're using the connectivity matrix and you're using those to insert the entries of the element stiffness matrix in the right spot. So yeah, that should work. Okay, so Jenna, so there shouldn't be any need to use +1, +2, +3. We only did that for the frame code just because each node in our frame code had more than 1 degree of freedom associated with it. Here, every node only has 1 degree of freedom, so you should only have 9 lines. So when you're adding the entries to the global stiffness matrix, you should only have 9 lines of code there. And you should just be using combinations of IND1 and IND2. There should be no need for +1, +2, +3, any of that stuff.
I mean, you're just looking, because when you're here around this point, you just change it. You're not gonna say.
Yeah, because you wanna give it balance. I don't know. You're gonna have to get that clicking. Yeah, it's a code of, It's still in there.
Class, I do a MATLAB related question. You can help me.
Sure. I can take a look at it.
It's. How do I make? So is there a way to add a zoom in feature?
Only for, what, if you use
Yeah, I've never heard of it. Yeah, it's basically taking on the data.
I could search it up. Try, yeah, I'm not sure. Try those. There's no conversation right there, so. You just need to compare on this one. So the total line error depends on the number of nodes. So we can get it.
Yeah, I was looking at those.
So one thing that, this is the richness, so this is the correct one. Yes, okay. So one thing to note about this, that it's gonna be actually really fun. Well, it's not, it is possible, but kind of in the default. Oh, yeah, so what's unique about this node, it's very, it's kind of like this edge. It's kind of cheap, right? So what's this edge right here? This edge, this edge was saying we should have fine. So this node, right, so technically there's only the seven. Right. So yeah, think about it. The difference is that was still here. This one here. So that's one that's not clear. That's actually one of the. Sometimes they can be much needed, like you preserve this. And so you can put these in slides. But most people are gonna end up. So this, so the situation like this. I think that's a really virtually. Normally this.
Well, yeah, I guess.
So both.
Okay, and if you have to find out, it's just the reference. Okay. Yeah. I'll give it.
And so they finish this one, but after it works, and then once you're done with the house, go down. Which goes. So it's gonna be more geared towards.
Then he said, whatever. Okay, we're doing this on a separate. We're doing something. Okay, whatever value, whatever the value. That's all I need. It's a little bit. Everybody's like that. And should match what you're doing. Notice how you're using more like. Whatever you modify.
Okay, this. What it is. We're gonna get this answer. Equal. Okay.
This signal value.
So
I don't have
Normally I would.
No, it's certainly one on the online. Even that, like this one, my students.
All right, guys, so we're out of time. So remember, I do have office hours next week. So office hours are gonna be at their normal times, Monday, Tuesday, Thursday. But they're gonna be virtual. And so if you need help next week on your project, just come to virtual office hours then. But just one more time, I know there's a couple questions in the chat. I'll address those in a second. But you know, just one more time, I just want to say thank you guys for a great semester. I know the beginning of the semester was kind of weird with the strike and everything, but I appreciate you guys being patient with me. Appreciate you guys' energy, your efforts. So thank you guys. Hope you guys have a good summer. I'll probably be teaching more tech electives in the fall, so I might see you guys then. But yeah, hope to see you guys around. All right, Roger. Yeah, so that error is it's about what you expect, but there is a reason that there is a little bit of error, and so I would my hint for you is to look at the corners. You don't have to change anything. So that error of 107 is expected. That's the correct answer, but there is a reason why there's a very small difference between the plots. So that's all I'll say. So I want you to kind of look at the plots carefully, think about where those nodes are, the corner nodes, and think about why there would be a difference between your solution and the reference solution. Okay.